Now in this particular session, I'm going to talk about what do you mean by the algebraic multiplicity of the roots of the characteristic polynomial. Okay, so let's talk about this. Now you know that when we get a linear operator and we try to find the characteristic polynomial of the linear operator. Okay, that means what you can do, you can find the matrix representation of linear operator, and then we can form the characteristic equation. Then we get a characteristic polynomial accordingly, and we try to factorize it to solve it. Okay, the factorization is what that means, a kind of splitting of the polynomial into some factors, and that splitting is actually happens with respect to the field on which the vector space is defined. For example, let me put the definition first of all. You will understand what I actually mean. This concept is actually very important. Probably you recall that P of F is the set of or vector space of polynomials of all degrees. PF is the set of vector or vector space of polynomials of all degrees. Okay, so this is a vector space, you know very well, and its basis is given by this set. Okay, now a polynomial ft in this vector space PF splits over F if there are scalars C, A1, A2, AN. They may not be distinct from one another. In the field capital F such that this polynomial ft can be written as C into T minus A1, T minus A2, T minus A3, AN. Okay, this is very important fact, and you have to keep this in mind. When we factorize something, this factorization is being kind of splitting the polynomial into several factors, and that splitting is done with respect to the scalars chosen from the fields. Okay, now if you talk about a polynomial, then that polynomial, if it can be factorized, we have just learned the factorization process, but we have to keep in mind that in which particular field this factorization is possible. Okay, that is actually very important. For example, suppose while factorizing a polynomial of this kind, say ft is equal to t square minus 1, and suppose the corresponding field capital F is the set of real numbers, we can easily factorize this as t minus 1 into t plus 1. Okay. This factorization is possible. So here the splitting has been done, splitting into factors. Splitting into factors have been done in the field of real numbers. In the field of real numbers. Okay. And if I try to correlate this particular example with the definition given, here C is 1, A1 is 1, A2 is minus 1. Say in this manner. So if I want to write it the way by which the definition has been written, we can write it as 1 into t minus 1 into t minus 1 like this. Now suppose we are considering another example where I have chosen another function, say gt, which is given as, say for example, after solving the polynomial, after factorizing the polynomial, we have got this kind of thing. Okay, two factors have been obtained, t square plus 1 and t minus 2. Now this factor t square plus 1, you know, just look at this factor. This factor, if we keep ourselves in the field of real numbers, this cannot be, this factor, this particular term cannot be splitted, in the field of real numbers, in the field of real numbers. Okay, rather if I choose the field f to be set of complex number, then gt can easily be factorized as the following. We can write it as t minus I into t plus I into t minus 2. Okay, this factorization is possible, the splitting is possible only if we consider the field of complex number, and it is not possible if we consider the field as the field of real numbers. So and in the field of complex number, we can write it as 1 into t minus I into t plus minus minus I into t minus 2. And here C is equal to 1, A1 equals to I, A2 equals to minus I, and A3 is equal to 2. Okay. And that is what we actually call as the polynomial splitting over some field capital F. Here the polynomial, the coefficient of the polynomial has been chosen from the field capital F actually. Okay, you know this very well. Now why this is important is because of the following fact, and the following definitions will also be useful in this particular regard. First of all, why this fact is so important, the theorem that I'm going to state over here. The theorem says that the characteristic polynomial, of any diagonalizable operator, highlight this point, any diagonalizable linear operator splits. Characteristic polynomial of any diagonalizable linear operator splits. What does this mean? This means that we are considering two statements over here. Statement 1 says that, suppose we are naming the statement 1 as P. It is saying that T is a linear operator which is diagonalizable. And statement 2 is Q T splits in some field. Okay. So these are the two statements. The theorem is saying that P implies Q. So if you have a diagonalizable linear operator, it will split in some field. But the converse of this theorem is not true. Is not true. Why? It means that suppose we are getting a linear operator. We get linear operator capital T which splits. It does not imply always that T is diagonalizable. We'll try to understand this particular logic with the help of a problem. Okay. So it means that the statement Q that I have written over here, if P implies Q, it is true, but Q implies P, not always. It is not in general true. Not always true. Yeah. So this particular thing, why this splitting is important, is actually important because this splitting of the polynomial in some field has something to do with the diagonalizability of the corresponding linear operator. Okay, so next I'm going to put a definition over here, which will be required for our calculation. The definition says that let lambda be an eigenvalue of a linear operator or matrix with characteristic polynomial ft. Then the algebraic multiplicity or simply it is called multiplicity. Okay, of lambda is the eigenvalue, remember, is the largest positive integer k, for which t minus lambda to the power k is a factor of ft. Okay, so if lambda is the eigenvalue of the linear operator or matrix with characteristic polynomial ft, The algebraic multiplicity or multiplicity of this eigenvalue lambda is the largest positive integer k, for which t minus lambda to the power k is a factor of ft. For example, if I consider the matrix 0, 1, 1, 0, we know this matrix is the Pauli spin matrix. Okay. And what are the eigenvalues of this matrix? Let us try to find out its characteristic polynomial very quickly. 0, 1 minus 0, 1, 1, 0 minus lambda characteristic equation of this matrix of this sigma x is lambda 1, 0, 0, 1. Determinant of this should be equal to equal to 0, which is 0 minus lambda 1 minus 0, 1 minus 0, and 0 minus lambda. Determinant of this, which is equal to 0, and that is lambda square minus 1, which is equal to 0. And you see, we can write it as lambda minus 1 into lambda plus 1, which is 0. It is a 2 by 2 matrix. This 0 by 0, 1, 1, 0 is belonging to M2 cross 2, and the field is suppose R. So here in this particular case, the splitting is possible. The splitting is possible in the field R. The splitting is possible in the field R. Okay. And how many eigenvalues that we have got over here? The eigenvalues are lambda equals to lambda 1 equal to 1 and lambda 2 equals to 1. Okay. Now just look at the factor that we have got over here. This came with respect to the factor lambda 1, lambda minus 1, and this with respect to the factor, sorry, this is lambda 1 equals to 1 and lambda 2 equal to minus 1. This happened for the factor lambda plus 1 in the characteristic equation. Yes. Lambda 2 equals to minus 1, lambda 1 equals to 1. This happens with the for the factor lambda minus 1, and this comes for the factor lambda plus 1. Okay. What is the power? What is the power of these two factors? Here the power is 1. Here the power is 1. Therefore, by the definition, eigenvalue 1's algebraic multiplicity is 1, and eigenvalue minus 1's algebraic multiplicity is 1, and so on. Okay, this is what we call as the algebraic multiplicity of the eigenvalue of the characteristic polynomial corresponding to the matrix representation of the linear operator. Okay, so here in this particular matrix, Pauli spin matrix sigma x, the splitting is possible, and you also know that this particular matrix is, I separately showed that this matrix is also diagonalizable matrix, and therefore you know every diagonalizable matrix, if an operator is diagonalizable, its characteristic polynomial splits in the field, in the respective field. Now there comes the next definition, which is also very important. The definition goes like this. Let capital T be a linear operator. Let capital T be a linear operator on a vector space, W V, on a vector space V, and let lambda be an eigenvalue, of capital T. Define E lambda containing such vectors of V so that Tx equal to lambda x. Tx equal to lambda x. That is, it is the set which is null space of n t minus lambda iv. Okay, the set E lambda is called the eigenspace, of capital T corresponding to the eigenvalue lambda, okay. And E lambda is the subspace. E lambda is the subspace of V consisting of the zero vector and the eigenvectors of T. Zero vector and the eigenvectors of capital T. So E lambda is actually an eigenspace, is a kind of subspace of the vector space, and it may contain the zero vector. It is not like that it contains only the eigenvectors. It may contain a zero vector. With respect to the zero vector and the eigenvectors, E lambda becomes a subspace of the vector space. Okay, so you see, just look at the set. E lambda equals to x belongs to V. It is not mentioned that x needs to be non-zero. Any vector x which satisfies this equation, Tx equal to lambda x, will belong to the eigenspace E lambda. And if there are two eigenvalues, there will be two E lambdas. This space will be dependent on the eigenvalue that you have obtained during the calculation. Okay, we have done sort of this kind of calculation earlier in my earlier class. You have done it by yourself also. This theorem is also very important, that let T be a linear operator. Okay, on a finite dimensional vector space V, and let lambda be an eigenvalue of capital T having multiplicity say m, then dimension of E lambda will lie between 1 and m. Very important theorem. What is dim of E lambda? If you can recall, dim of E lambda is actually the dimension of E lambda. Because E lambda is a subspace, and therefore it will have some basis in it, and that basis, the number of elements contained by that basis, will be the dimension of this particular eigenspace. Okay, so eigenspace will contain all the eigenvectors as well as the zero vector. Now let's consider a problem that I have chosen this problem, and from this problem, I think everything will be clear to you. What is being taught about here? Let capital T be a linear operator. Let capital T be a linear operator defined on P2R. What is P2R? Set of all polynomials of degree less than or equal to R. Sorry, yeah, less than or equal to 2. Not R, it is 2. This is P2R. And this linear operator is defined on P2R by this operation. D of fx is ddx of fx. This is a very well-known operator, and we have probably worked on this. Basis of P2R, we all know that, is containing 3 elements, 1, x, and x square. We will try to find out the linear operator. With respect to this, we'll try to find out the matrix representation of this linear operator. So I am showing you once again the calculation. What we do, we try to find out the transformation. I will try to look at the transformation when the T acts on the basis elements. So T1 is actually ddx of fx at fx equal to 1, and which is equal to 0. And this can be written as 0 into 1, 0 into x, 0 into x square. T of x means ddx of fx when fx equal to x, which is equal to 1. That means 1 into 1 plus 0 into x plus 0 into x square. T of x square means ddx of fx when fx is x square, which is twice x, 0 into 1 plus 2 into x plus 0 into x square. Okay. And so capital T, matrix representation of T with respect to beta, is given by, we write all these elements in column wise, as we all know. So we'll write 0, 0, 0, then go to the next one. We get 1, 0, 0, come to the next 0, 2, 0. This is our matrix. This is our matrix. Okay. One another thing, if we define, this is extra, it will be required for us for the calculation. If we define identity operator, on P2R as I of fx is equal to fx, another operator that I'm considering over here, then I of, quickly I'm writing it as I of 1 will be 1, which is 1 into 1 plus 0 into x plus 0 into x square. I of x will be x, which is 0 into 1 plus 1 into x plus 0 into x square. I of x square is x square, which is 0 into 1 plus 0 into x plus 1 into x square. And therefore, the identity operator in this case with respect to P2R and its basis will be like this. That we all know. It is quite trivial. Okay. Now, what we are going to do, this is the first phase. We have got a linear operator and we have found its matrix representation. The next phase is to find out the characteristic polynomial of this matrix. Characteristic polynomial of this matrix will be obtained as the following. Determinant of this minus lambda I beta, okay? Beta is the basis of it, remember, which is equal to 0. And this implies we'll get the polynomial as, I'm quickly writing, 0 minus lambda 1 0 0 0 minus lambda 2 0 0 minus lambda. I hope I have not done anything wrong over here. And if I find the determinant, now this will be minus lambda, this will be minus lambda, we'll get something as minus lambda into minus lambda 2 0 minus lambda. Okay, no problem. Then we'll get 1 into 0. So this part will be 0. We'll get something plus 0 into 0. So that part will be 0 also. So from there, we are going to get minus lambda cube, which is equal to 0. Now, if I want to write this minus lambda cube is equal to 0 in the form of splitting of the characteristic polynomial, you can write it as minus 1 into lambda minus 0 to the power 3, which is equal to 0. I am trying to write it in the following manner. C into t minus a1, t minus a2, dot, 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 t minus an. Okay. So from there, we actually get the eigenvalue of t beta is 0 with algebraic multiplicity 3 with algebraic multiplicity 3 because of this factor. Okay. Now for lambda equal to 0, the eigenvector equation, we all know it is given as t of beta into some vector. Eigenvalue is 0 multiplied by this factor. So I've just written here AV equal to lambda b. This has been written over here. This implies you put your t beta is 0 1 0 0 0 2 0 0 0. Put this, its order is 3 cross 3. To put a vector v1 v2 v3 over here, which should be equal to 3 cross 1, and that would be 0 0 0 0 0 0. What do you mean by 0 0 0? 0 0 0. What do you mean by this? Is it a matrix? No, it is a 0 polynomial. It is 0 into 1 plus 0 into x plus 0 into x square. That is what we have put over here. What is v1 what is v1 v2 v3 over here? Is it a matrix? No, it is a polynomial. v1 into 1 plus v2 into x plus v3 into x square. So remember, don't confuse yourself. And if I solve it, we get v2 to v3 0, which is equal to 0 0 0. Okay. And this implies v2 equal to 0, v3 equal to 0, and 0 equal to 0. So actually, therefore, I'm writing over here, therefore, the eigenvector v1, v2, v3 is actually V1 has got some choice, infinitely many choices because of this equation. V2 is strictly 0, V3 is strictly 0. This is the eigenvector. Okay. And this equation is nothing but, this is nothing but V1 into 1 plus 0 into x plus 0 into x square. Okay, this is the polynomial that we have got over here. The set of eigenvectors, the set of eigenvectors is t into 1, 0, 0. As we all know, t not equals to 0, t belonging to R, field of scalar, because eigenvectors are always non-zero vectors. And if we construct the eigenspace E lambda, that E lambda will be t into 1, 0, 0, t belonging to R. Now, probably you have understood what is the difference between these two. Here, t not equal to 0 condition is not present. What is 1, 0, 0? 1, 0, 0. What is this? This is 1 into 1 plus 0 into x plus 0 into x square. Therefore, the basis of E lambda is, say for example, I'm considering B E lambda over here. Lambda equal to 0. Remember, lambda equal to 0. This basis is containing only one polynomial, which is 1. Just this. So E lambda has a basis this. This is the basis. And therefore, dimension of E lambda is equal to 1. Now you see, I wrote this in the theorem. Where is that theorem? That if T be a linear operator on a finite dimensional vector space V, and lambda be an eigenvalue of T having multiplicity M, then dimension of E lambda will lie between 1 and M. Here, lambda equal to 0 is the eigenvalue. Its multiplicity is 3. And dimension of E lambda, that means dimension of, I must not write E lambda, rather in place of E lambda, I must write, because the eigenvalue is 0, so I must write E0. E0. So here the dimension of E0 is actually coming out as 1, which is satisfying the theorem. And not only this, and there is no basis of P2R consisting of eigenvectors of capital T. We have not found any basis of capital T any basis of P2R with respect to capital T which contain the eigenvectors of capital T. We have not found any such basis, and therefore capital T is not diagonalizable. Now just look at this important part. Go to the first theorem. In the first theorem, it was said that T is a linear operator which is diagonalizable, and T splits. Okay, but the converse is not true. If for a linear operator, it splits into factors in the field, it may not be diagonalizable. So here you see for this particular linear operator, splitting was possible, but the operator is not diagonalizable. So which justifies that the converse of the theorem is not always true. Hence proved. So this much for today. Need not join once again. Let's meet in the next class.